Good afternoon, everyone. My name is Ismael, and I am the founder of Lagrange Labs. So what is Lagrange Labs? So Lagrange focuses on building proving systems and proving infrastructure that make it efficient to verify large-scale computation over on-chain state. And why is this useful? Well, it allows you to build applications that are far more expressive and far more data-rich than what you can today. So let's take a step back to start with and talk a little bit about verifiable computation, VC, broadly. So verifiable computation, or zero knowledge, as a lot of people like to call it, allows you to shift the safety of a computation away from a lower trust proving environment onto a higher trust verification environment. In the blockchain context, we typically see this embodied in shifting where computation is verified away from an off-chain actor who executes that computation and onto an on-chain verification contract where that computation is verified as part of some application function. So what are the applications of zero knowledge that we're seeing in the blockchain context? And this should really not be new information for everyone at Zero Knowledge Day. But the early question that we saw people tackling with ZK applications are really, how do we increase the abundance and the privacy of block space? But over the last year, and maybe 18 months, we've seen a new shift away from that question onto a new question, which is, how do we increase the safety and expressivity of computation, the safety of the data we can access for that computation, and the expressivity of the functions that we can run? And this is where we've seen these new generation of ZK applications, the co-processors, the VM extensions, the non-EVM ZK execution environments, ZK interop, and more. And so let's break down both of these new trends that we're seeing. So what do we mean by safety of data access? Well, is the data that an application has predicated its core functions on derived from a source with the same safety as the underlying execution environment? So is my application that derives its safety from Ethereum consensus relying on data supplied by some off-chain oracle? Is a interop protocol core to the function of my application deriving its safety from a proof that's verified on Ethereum consensus or from elsewhere? What do we mean by expressivity of transactions? Well, if we look at the current embodiment of transactions that we see on-chain, they typically are simple exchanges of value or simple state transitions in a contract. When we look at the future state that these new ZK coprocessors or VM extensions are unlocking, these are large asynchronous computations that can be executed elsewhere and verified back in the execution environment. So think of inference of an ML model. Think of query over a large subset of on-chain state. Think of maybe a big data scale computation over historical on-chain transaction, receipt, or storage data. These are the type of things that can run asynchronous and then verified back in the core execution environment. And so this gets to what Lagrange Labs does. So Lagrange's ZK MapReduce stack is optimized for very large-scale verifiable computation over historical storage, receipt, or transaction state. So to put this in the lingua franca of now, think big data co-processing. And so what does this leave us with, and why is this useful? Look at on-chain state today. Fundamentally, what you see is a fragmented data lake. There are disparate application states over rollups, L2s, different L1s, modular context as well. And what you see is that modern applications are unable to query across a meaningful amount of that state. So you can't derive your pricing for your lending app by an analysis of on-chain state. You have to rely on an off-chain feed to synthesize that for you. You can't have a meaningful search over the owners of balances in ERC20 contracts because you can't have sufficient depth on your query. You'd have to iterate through all the owners. And so this is where ZK MapReduce and our team's work comes in. This is a proprietary proof construction developed by our team that is optimized for concurrently proving large-scale batch proofs and dynamic data parallel computation. Things like MapReduce, Spark, RDD, and SQL. The types of things you'd run over your Web 2 data lake, now applicable to on-chain state. And so what this lets you do is to structure proofs that have a very rich relationship with the underlying data of a chain that have a high depth of historical data and a high breadth of cross-application or cross-chain data that can be recursed or folded together and merged to one composite proof. And so what is required to generate a proof? Really 4 principal components: a block header, or more than one block header, of a source or series of source chains, a specific range of storage slots and block headers you want this computation to run across, and then some computation that's data parallel. SQL, MapReduce, Spark, RDD, something along those lines. And then finally, a verification contract on the destination where you want that proof to inherit its safety from. So how do we do this, and what is kind of the secret sauce behind our proof constructions? So the core of this is a vector commitment scheme our team developed called rec proofs. So we presented rec proofs for the first time at Stanford Blockchain Conference in the summer. And what this enables us to do is to construct batch proofs over very, very large subsets of a commitment, and to have dynamic computation over that data concurrently with the proving of that inclusion. And what rec proofs have, as compared to other vector commitment schemes, is this new property of updatability. And this might seem trivial of why would you want to update your proofs, but we'll very quickly see why this matters a lot when structuring proofs over blockchain data. So think about wanting to derive the standard deviation of an asset between a range of blocks. Let's say block B to B minus K. And you want this standard deviation, so that you can do your Black-Scholes and compute your volatility, to be derived from on-chain dexes rather than some off-chain trust me style source. And so you want to structure your proof such that it proves the inclusion of the prices and then calculates a standard deviation across that range of K blocks. But we're on a blockchain, so new blocks come in. And so 12 seconds or maybe less in a modular context or an L2 context, you would have to recompute this proof from scratch. So you would, in essence, have to remove the oldest piece of data in that buffer and add the new piece of data for the new block, which forces an entire recomputation that's linear in complexity and time with respect to the size of the data you're computing over. That is intuitively not a very effective paradigm for data structures that continually update. So this is where rec proofs come in. You can structure a rec proof over a very large commitment of data, and then you can update the underlying proof when the data that you're computing over changes. So for things with low entropy, like this proof we just talked about over a range of K, you would only have to make a logarithmic time update by removing the oldest data and inserting the new data, and you can change the computation along the path without necessitating an entire recomputation. So proving time is an order of magnitude faster. And so this is very, very good for blockchains because they are in principle low entropy when you look at storage state. The majority of storage slots don't change across successive blocks. And when you're structuring proofs across large ranges of blocks, the majority of that data and that buffer is going to be consistent across the marginal run of a proof. So you don't have to actually recompute duplicate work every time you want to prove something. And so this new principle of updatability in proofs allows you to scale proof computation not through recomputation, but through composition of previously computed proofs. So this gives you an incredibly low overhead on supporting new chains and supporting new computation frameworks without requiring you to have the traditional proving time complexity that naive approaches have. And so we have benchmarks from the paper in SBC, and the first version is 135 times faster on recomputing than naive approaches, but we expect this to be in the order of thousands when we talk about MPT trees, when we talk about production data. And because this is data parallel, and we can go fundamentally, embarrassingly parallel on all of the computation that we do, we can increase our speed by up to 10x by distributed proving. And the verification time, since these are very small proofs that are composed together, is substantially lower too, as is proof size. And so we're going to discuss very briefly a few applications that I think are very relevant when we kind of think about the future state of coprocessors and ZK compute with respect to on-chain data. So the first is something that we like to call in our team digest transformation. So what is digest transformation? Think of this like ETL, extract, transform, load, for on-chain data. The majority of data in the blockchain context is encoded in formats that is not friendly for booster rollups or ephemeral rollups or coprocessors to compute over. So what this leaves you with is downstream complexity that gets pushed onto any ZK application that wants to compute something meaningful over on-chain state. What you can do with a digest translation is you can prove that the unfriendly Ethereum structure is equivalent to some new structure that is faster to compute over. So imagine you have a booster rollup that wants to compute over some subset of the MPT tree. Instead of having to continually compute over the catch-ax and the RLP encodings with high proving time, you can simply put a rec proof on top of that entire portion of the tree and iteratively prove that that's equivalent to some, let's say, Poseidon-Merkle tree. All of a sudden, your booster rollup just has to verify the proof from the rec proof, and then only has to compute over that new structure. Meaning that you can take the output of our coprocessing, and you can use that as an input, in fact, for another coprocessor, booster rollup, or ephemeral rollup. And you can make the second application substantially faster by being able to leverage the updatability of the proofs of the underlying data. So to get something a little bit more fun, think about verifiable rewards. This is another one we're very excited about. Things like contract secured revenue, where you want to issue sequencer fees or some financial reward based on on-chain activity. And you want to do so iteratively without having to push the regulatory issues and the agency issues onto some party who becomes the arbiter of reward issuance. So in these situations, you can structure this computation over large subsets of the commitment, and then you can prove that when relevant. So the next one is another somewhat in the weeds primitive, but it's very applicable to things that use BLS key aggregation and have to prove APK aggregation on chain. So if anyone here is familiar with BLS aggregation, the complexity typically in proving time comes from the aggregation of public keys rather than the verification of the aggregate signature, which is a linear time, which is a constant time operation. And so with rec proofs, you can prove the inclusion of some subset of signers in a commitment, and then you can update the proof of that aggregation as the signer subset or the signer set overall changes. And so what this allows you to do is to iteratively change the BLS aggregation as you change the signer set or signer subset without having to recompute all of that. And that's great for applications where the entropy between successive signer sets or signer subsets is very low. Now, another primitive that we like to talk about is something called full storage queries. Most data in smart contracts today, as most of the developers know, is encoded in mappings. So you have some index and then a bunch of values, and a bunch of secondary index or tertiary index. So it makes it very difficult to query over anything that isn't the primary index. So if I want to figure out, for example, all NFTs that are blue in some collection, because I have some second-order GameFi application that needs that, you can't really compose with that initial contract very well, because the data that you require can't actually be searched. You have your index, and then you have your owner, then you have associated metadata properties, and you can't actually figure out what those associated metadata properties are without just looping and iterating through the entire collection. And this is the same principle with the ERC20s if you want to check how many users have a balance greater than n, or how many users' balance has changed between some ratio over the last 2 weeks, 2 months, et cetera. And so what you can do with this is you can just structure a proof over that entire subset of memory corresponding to the mapping, and then you can just update that proof and compute over it. Finally, you can build some very cool exotic DeFi primitives. I'm not a DeFi developer, or a very good one, but there are a lot of very good ones. And when you can start actually accessing the on-chain data that you use to start deriving things like volatility, standard deviation directly from on-chain state rather than from off-chain sources, it decreases the risk profile substantially of anyone composing with or building with a DeFi application. So if anyone wants to learn more about some of the technical underpinnings behind the talk today, I would recommend you look at rec proofs, the paper that we discussed briefly earlier, as well as some recent work our team put out involving the application of folding to rec proofs in our ZKMR stack, where we turn IVC Nova into PCD-based Nova. So thank you, everybody. And now I think it's time for questions. Questions?
Hi. Do you like the direct proof actually like use the Nova like for underlying to generate the proof?
Yeah, that's a good question. So RecProof supports any proving system that has recursion or an abstraction of recursion like folding. And so as long as you can have the same arity in your proof composition that you have with your underlying data structure you're proving over, then you can use RecProofs with what you're using. So you can use it with Plonky2, you can use it with Nova, you can use it with Supernova, you can use it with Starkey, you can use it with anything, really.
So I might have one more question.
Yeah.
Okay, like for Halo 2, especially for the Halo 2 or PSE4,
Yeah.
so it's not friendly with the recursion. So yeah, so I think like it will be a big problem for your project, or you have any solution for this?
For PSC, I mean, I think PSC, so I think Halo 2 doesn't have good recursion time, it has aggregation time. So I don't think that something that requires iterative updates to a proof with this format would be well suited for Halo 2 as a proving system. But I think there's other things that Halo 2 can do well.
Okay, thank you.
Of course. Good questions, thank you. No one else?